Okay, so we have the third talk in this session by Tanja Hinderer from Institute of Theoretical Physics in Utrecht University. And Tanja will talk about probing gravity with gravitational waves from Inspirals.
Thank you very much. Yeah, so the plan is to follow up a bit on the excellent overview that Emanuele Berti gave in the beginning. But here going into kind of two examples in a bit more depth of how when we break some assumptions of GR, new phenomena can arise in gravitational waves and what we can learn from them. And in particular, I want to consider two types of classes of theories. One is this Einstein scalar Gauss-Bonnet theory that Emanuele described in detail. And also, of course, we also want to know not only how does gravity behave for vacuum solutions like black holes. Let's say for the moment, we don't consider the the exotic object, but we also want to know how does it actually couple with matter and test that in detail. So we need neutron stars. So I will say also something about this in a bit. Yeah, and so just to come back to the point, as Emanuele already described, of course, kind of the most agnostic thing you can do, since there's a plethora of possible gravity theories. We know GR works well on scales that have been tested so far, I mean, at least to some precision. So the easiest thing to do is to do some consistency tests or introduce some small deviations and constrain the deviations from GR. But then what is also needed is then some theoretical underpinning to connect that actually, what do these deviation parameters, for instance, mean for the underlying theory of gravity? So we actually also need some examples of waveforms in modified gravity theories. And even if we find that GR is maybe consistent, we want to understand, yeah, what about gravity at a fundamental level are we learning? Not just that Einstein was right up to the scales we have tested, but what are we learning? As Emanuele mentioned, GR makes a lot of assumptions as stated in Lovelock's theorem. So if we break one of these assumptions, what feature would we see in gravitational waves and so on? We want to kind of really dig down, what are we learning at a fundamental level? Also, you see in many examples, as also Emanuele discussed, that it's quite, in many classes of theories, there are new degrees of freedom like scalar fields that get added. But scalar fields are also invoked, for instance, to explain dark matter, to explain inflation and so on. So certainly we also want to be able to distinguish, well, is the scalar field now just an extra matter content in the universe, or is it involved in mediating gravitational interactions? Or if we want to put constraints on these scalar fields, do they differ and so on? What degeneracies are there between sectors of physics? So in any case, the point is we do want some examples of waveforms in theories of gravity that break some of the assumptions of GR. So as a first example, I want to go back to Einstein scalar Gauss-Bonnet gravity, which Emanuele already described. So in that sense, there's a higher curvature correction to general relativity, so that general relativity emerges as kind of a low curvature limit of a more fundamental theory. And this curvature correction is dynamically coupled with a scalar field, which is necessary so that it has any effect at all, because this curvature correction is a certain invariant that involves different combinations of curvature quantities. And the main thing to note in this case is that in that case, black holes can acquire scalar hair. So that means there can be a scalar condensate forming around black holes that extends through the horizon and can be relatively stable there. So what are now the consequences when we have these scalarized black holes in the binary system? Well, there are many effects of scalar fields that are quite universal in some sense that can be described for any scalarized object. For one, now there are not only gravitational waves, but also scalar waves. And we don't measure scalar waves directly, but they take away extra energy from the system. And the key point to note is that scalar waves can already, at least in this case, start at dipolar order, whereas gravitational waves start only with quadrupolar and higher. And yeah, all of these kinds of leading order scalar effects can be described in terms of the scalar charges of the objects. And here the charge is in quotation marks because it's not an independent parameter, it's fixed. Once you fix the theory you're considering, you compute what is the scalar charge. It's defined as the fall off of the 1/r piece of the scalar field at large distances. Okay, so this is already quite well established, but now we also still have to know what are the effects of the higher curvature corrections, not just these extra scalar fields. And we should take into account that the scalar clouds also interact with each other. And in particular, the leading order interaction, at least when they are far apart, is that there are tidal effects between the scalar clouds, because we saw before the scalar field falls off like 1/r from one of the objects, which is exactly similar like a gravitational field. So the other object, the cloud, feels a gradient in scalar field across its cloud size. So it responds by deforming. And in this case, the deformation starts already at dipolar order. So we then have an induced scalar dipole moment, which I denote by QIS here for a scalar. And that's proportional to the scalar tidal field, which is just the gradient in the scalar field sourced by the companion, by some extra tidal deformability, love number, whatever you want to call it, polarizability. All of these are used interchangeably for this response coefficient. And then you can calculate this coefficient again in terms of parameters of the theory. Interestingly, so this now depends on second derivatives of the coupling function. So depending on what coupling function you choose, this might not be present if it has a vanishing second derivative. But in other cases, this effect might be there. And the interesting thing is that, when you compute what is the effect in gravitational waves of these tidal interactions, they scale in the same way with frequency as these explicit Gauss-Bonnet higher curvature corrections. So you should take into account both of these phenomena in the waveform models. What is also interesting is that, well, okay, first of all, we should check that these analytical results are reasonable by comparing, for instance, with numerical relativity simulations. These are done by Helvi Vitek already some time ago, where she took a binary black hole merger spacetime from DR as the source of a scalar field in Gauss-Bonnet gravity and computed the scalar field. So we did the same thing on the analytical side and can see now these higher curvature corrections, higher post-Newtonian scalar field results. Do they bring us a bit closer to numerical relativity? Well, it's not yet very good, but at least a step in the right direction. Okay, and what is more also interesting is that, well, I mentioned scalar radiation starts at dipolar level. So kind of that is important at low frequencies. When the binary is far apart, it's more important than gravitational waves. So, but on the other hand, when the system is close together, gravitational waves are dominating the energy losses. And so we have kind of the early Inspirals, scalar dominated, the late Inspiral, gravitational wave dominated. And interestingly, if we look at the phase evolution versus frequency, how it depends on parameters in these two regimes, it's very different. And also one can dissect it furthermore in terms of are the tidal effects larger or the higher curvature and so on. Let me not get into this, but just to say, for instance, here is the mass ratio dependence is different in the early Inspiral versus the late Inspiral. So now the question is, where does this turnover happen? And is it something that we should look for in detectors? Well, it of course depends on what parameters you choose for everything. But it could be, in some cases at least, that one can arrange for things that in LISA would see the early inspiral mainly, then ground-based detectors might see the late inspiral. So this is also something to be aware of. Maybe for multi-band sources, one might have to be a bit careful how to connect between the different regimes. But of course, as I mentioned, caveat is this all depends on parameters. Okay, so this is kind of what I wanted to supplement to what Emanuele said about Einstein scalar Gauss-Bonnet gravity. Now I want to go also to neutron stars, because as I mentioned, we also want to test how does gravity couple with matter. But of course, when we have neutron stars, there are all kinds of extra complications. We don't know the equation of state of the matter. We don't know if there are phase transitions. There's also now a lot of interest in neutron stars accumulating dark matter in their interiors. And now we are also coming saying, well, maybe there could also be modified gravity matter couplings coming. So, well, as a first step, we want to understand what would these modified gravity matter couplings do to a neutron star. And in this case, let's not consider the higher curvature corrections because there are extra complications. Let's just have the extra scalar field. And in this case, again, we have now some kinetic term in the action for the scalar field. We also have now, in the matter part of the action, the matter fields mix with both the metric and some function that depends on the scalar field. So what can happen again in this case is that neutron stars can scalarize. So there can be a scalar condensate forming. And in that case, the solutions can be very different from GR. Again, we have now the asymptotic scalar fields far from the neutron star falling off as 1 over r, but also there's now a constant that is not necessarily 0. If that's 0, basically you can get back to GR, but here we also keep it more general. And then already a long time ago, Damour and Esposito Farès computed neutron star mass radius curves and also how the scalar charge looks like and how it correlates with mass radius curves. What you see here is for 3 equations of state, different mass radius curves in solid is general relativity, in the different dashings is different parameters of this coupling coefficient beta 0. And you see in some cases there can be large deviations from the mass radius curve of GR, and it correlates with a large scalar charge that develops above a certain threshold. And this was also already well known that this kind of scalarization phenomenon is a really non-perturbative phenomenon. Above a certain compactness, the scalarization sets in. And how to see that it's non-perturbative is also quite nice. So here, this was for phi infinity 10 to the minus 3. So if it was perturbative, you might think, well, if I choose a smaller phi infinity, this effect should become smaller. But in fact, here I have 10 to the minus 6. The effect doesn't go away. It just makes all the features sharper. And there's a nice review article on scalarization by Daniela Doneva and collaborators explaining how you can understand this in terms of phase transition analogies and so on. But anyway, that is a bit of a digression. Now I want to consider what are the consequences for gravitational waves. Well, so again, I come with tidal effect. Sorry, it's the same theme over and over again, but now it's even more complicated. Because now we have not only the scalar tidal effects, but also we have tensor tidal fields for the neutron star. And because everything is very nonlinear coupled inside the neutron star, because that's really a strong nonlinear gravity region, we also have mixed scalar tidal and tensor tidal effects. So that means basically what I write here for the quadrupole response. For instance, the induced scalar quadrupole is, as one would expect, proportional to the scalar external tidal field with some scalar love number, but it's also proportional to the tensor tidal field with some different response coefficient, because if you put a tensor tidal field, but then you have all the nonlinear interaction between space-time, scalar field and matter in the interior, you also end up inducing a response that to the tensor tidal field in the scalar sector, and vice versa. So actually, you now have to deal with 3 different tidal deformability coefficients up to quadrupole. Plus, of course, you have the scalar dipole, but since we don't have the gravitational dipole, that part is kind of cleaner. Okay, then it's a matter of how do you extract it from perturbative calculations. Well, I don't have time to go into it. All the Mathematica notebooks are available, really. What is interesting, I'll finish up soon, is if we look at what these coefficients look like as a function of mass is, well, let's look at the tensor love number first. So the dashed line here is still the GR curve. And then this bump is kind of correlating with the scalar charge. Also here is a mixed scalar tensor tidal love number in orange, which is negative. So we have multiplied it by -10. Also, it's smaller. So that's interesting also that it's negative. And it also correlates with the scalar charge. But these other ones, even for when you're not in the scalarized phase, so when there's not this difference from the GR solution, you still have quite appreciable love. So this is something you don't have in the mass radius curve. For that region here, for instance, for these masses, you would have the same mass radius curve as in GR, but for the love numbers, that's no longer the case. They do differ. Okay, so just to finish up, now what's the effect in gravitational waves? Well, as I already mentioned, the tensor love number is negative. Also, some of these tidal effects between scalar influences come in with explicit negative signs. So taking everything together, one finds actually that contrary to what one might expect, the total tidal phasing is actually smaller in scalar tensor theories than in GR. One might have expected, since there are now all these extra tidal interactions, maybe there should be a larger tidal signal, but it's not the case. And of course, then it could be also degenerate with other physics, but that's something to be studied. So in conclusion, yeah, I've only presented some small examples of extra new effects that could arise. I think it's worth exploring some of these. Because also, yeah, we want to gain the most science from future observations for fundamental physics, of course, also all other physics, but yeah, then it makes sense to devote a bit of time even to exploring models that some of you might think are not very well motivated, but just to understand a bit better, yeah, what are we actually learning from gravitational waves? Because everything gets very non-linearly imprinted from fundamental physics of the source or even the propagation into ultimately the waveforms. So this, we want to still disentangle a bit more. So thank you very much.
Yeah, so towards the end, you mentioned that tidal imprints on gravitational wave emission would get somewhat dumbed down. Is that?
Yes, that's
okay.
correct.
But what about compactness as measured by Neisser-like experiments? Because you also showed the effect on mass radius curves.
Yes,
right?
the mass radius curve would, well, of course, it depends. So here is one example. Yeah, so here it's not so visible, but you can have regions where the radius decreases. But I mean, okay, these are also extreme couplings that are shown here. Yeah. So,
but so the coupling is universal. So all, I mean, to the extent that any neutron star is scalarized in this fashion, these fundamental parameters will be the same across neutron stars. Is that something I understood right?
That you would assume that. So this parameter beta is kind of in the coupling function. So this is the conformal factor that of the metric that couples with the matter. You have this coefficient. And this was just a choice of the coupling function. You could also choose something different, but presumably once you fix this, it should be universal. Yeah.
So it's not that bad.
Yes.
Yeah, so Tanja, I was a bit curious about one plot where you showed the NR simulation and with the scalar fields and now with the analytically, and you're saying that you are just catching up. Like I'm wondering what else is missing to match with the NR simulations, like in the analytical approach?
You're wondering what?
What is more missing in the analytical approach that's still not coinciding with the NR simulations?
What causes the remaining difference?
Yeah.
Oh yeah, because these are just, I mean, it's just to first post-Newtonian order, relative order. So it's a very low post-Newtonian order. We would not expect to have.
So some more terms are there, it means, right? Like.
Yeah, so it's more in terms of, yeah, is it completely crazy what we have calculated? More sanity check.
Okay, and one more short question, that does it affect the usual tidal love number also, this scalarization?
The usual tidal love
number?
number?
Does it get affected because of the scalar charge being present?
Yes. So the usual tidal love number, it was plotted here. This is the tensor tidal love number. And it does get affected for certain neutron stars with certain mass. Okay. And it still turns out, because one can then ask, yeah, what is the effect of all these love numbers on the phasing? And it turns out this tensor love number remains the largest effect in the phasing.
Go ahead. Thank you for the talk. I just have a question about the black hole scalar case. You said that the scalar radiation dominates early on at low orbital frequencies, and then the gravitational radiation dominates later. Is that just because the dipole radiation goes like omega to the 4th in the power, and the gravitational radiation goes like omega to the 6th? So they just cross at some characteristic frequency.
Yeah,
exactly.
Okay, hi. During the discussion of the Gauss-bounded gravity, you talked about some scalar losses. So does the similar thing happens in the tensor sector also?
Yes, so the tensor is also modified.
Is there a similar losses in the, like, as you talk about the scalar losses in the Gauss-bounded gravity? So something similar happens in the tensor sector also, and does that anyhow changes the MR relation? So like you showed the usual GR, and then we have a bifurcation in the when the scalar fields are present. So because of the losses, does that changes or gets modified somehow?
So I'm not sure I understand the question. So you're saying if there's no scalar field, then you have just the tensor losses? And if there's a scalar field, yes, then there's extra losses. So yeah, that can be.
Just was wondering, how do we think about the tensor losses? Because I can understand scalar losses, what does that mean? But when we talk about losses in the tensor sector, then how do we think about that?
I just mean losses of energy and angular momentum that is radiated. Yeah, sorry, that was maybe not clear. Yes. So I meant just energy losses, you know, when you use energy balance to calculate the chirp of the binary, those losses was what.
Okay, so thanks to Tanja once again, and